Hello, everyone. Thank you for joining us today for our live session. This is the March 30th, 2021 live session. Thank you for joining us. We know that people find us from all sorts of places. We run classes on Coursera and Udemy, and we are also on Twitch. So if you're joining us from any of those, welcome. Please ask your questions in the chat. I will grab them from there. I will let Professor Impey say hello to everyone, and we'll get started with your questions.
Okay, welcome everyone, and just give you a little heads up that we're going to keep our regular pattern of live sessions, but on Monday, April 12th, it's Yuri's night, the anniversary of Yuri Gagarin's first human space flight. It's actually a 60th anniversary, so quite a big one. I'm going to do an evening lecture for Steward Observatory, and we're going to put the information for how you could join that lecture. It's at 7:30 Mountain Time, Arizona time, p.m. We'll put the information of that into an announcement through the MOOCs, and also that week, the live session that we hold, which I think will also be on the Monday in the morning, our time, will just be about the topic of space travel. So that for the first time, we'll just have a Q&A that's totally dedicated to the occasion of Yuri's night, the first venture into space and the history and future of space travel. But otherwise, we're here for questions on all topics in astronomy. Ready for your questions.
Excellent. I am also excited about Yuri's night, and we will get that information soon. The first question is from one of our live participants. Lawrence would like to know if our Big Bang produced an asymmetry of matter and antimatter, would most other Big Bangs produce equal parts matter and antimatter, leaving behind only energy as expected, assuming that the Big Bang was a quantum event?
That's an interesting question, and so to unpack it a little, let's just talk a bit about the asymmetry in matter and antimatter that was present in the very early universe. We think that was asymmetry because otherwise microscopic physics in the lab is very symmetric, or the laws of physics apply equally to matter or antimatter. So the overwhelming abundance of matter in the universe has to be explained. The current explanation is that asymmetry arose early in the history of the universe during the grand unification, or the unification of three of the four forces of nature except gravity. So there are mechanisms that can explain a slight asymmetry, but they're not completely proven or tested with lab physics. Now, in that asymmetry, if with a small excess, asymmetry of matter and antimatter with slight excess of matter, then in the final annihilation of matter and antimatter leading to large number of particles, the small excess or residue of matter turns into the material contents of the universe, and we're left, as you would see, in a universe that has much more radiation or photons than it does particles or matter. And that's what we see. There's hundreds of millions of microwave photons from the Big Bang for every particle in the universe. So the question as to whether that might happen elsewhere in other space-times or other universes is an interesting one. And indeed, in the sort of multiverse concept, which emerges out of the quantum nature of the universe's origination in the Big Bang, it is indeed possible that other universes would exist or could exist, and they would be governed by quite different laws of physics. So there could be universes that did not have that antimatter asymmetry. And of course, in those universes, you'd only have radiation in the final annihilation of particles and antiparticles, and so there'd be no objects, there'd be no structures, there'd be no people, there'd be no planets or stars or galaxies. So if the laws of physics were like rolling the dice in these quantum events of other parallel space-times, then you could have radically different universes from ours. Unfortunately, we don't have an overarching theory for the multiverse that we can test to understand how the variation in the laws of physics might have played out in other space-times. So we're just left to speculate.
Excellent. Thank you very much. The next question is from an email from one of our students. Wendy Traver asks, is the cosmic microwave background the only remaining signature of the Big Bang, and what is its projected lifespan?
Well, the microwave background is the most convincing evidence of the Big Bang because that radiation still exists. It's been stretched by space-time expansion by a factor of 1,000 since it was released at the era of recombination, when the universe had a temperature of 3000 Kelvin. Now the temperature of that radiation is 3 Kelvin, so very cold microwaves. It's the best evidence, but not the only evidence of the Big Bang. The other evidence of the Big Bang is the abundance of helium in the universe. About 1 in 12 particles are helium nuclei as opposed to protons, hydrogen nuclei, and that's about a quarter of the mass of the universe is in helium. And since that is indeed produced in stars like the sun as part of their fusion, there's not been enough stellar evolution and ejection of helium into space to nearly account for a quarter of the universe being helium by mass. And so stellar evolution is completely inadequate to explain the amount of helium in the universe, but the Big Bang does it very well and naturally, as well as explain several other light element abundances. So I'd say that is a second very strong piece of evidence for the Big Bang, because otherwise there's no explanation for where the helium came from, why there's so much of it. And the third evidence, of course, is the expansion of the universe, the recession or redshift of galaxies that we see, which you can trace backwards, like running a clock backwards, to an earlier hot, dense state. And so running that clock backwards points directly to the Big Bang. I think there was a second part of the question that I missed.
Sure. Basically, what's the projected lifespan of the cosmic microwave background? How long will we be able to see it?
Okay, so let's treat that as a separate question. The microwave background radiation from the Big Bang is, the universe is embedded in this radiation. It's everywhere around us. It doesn't have a location. It doesn't have a direction. It was released in the space-time of the universe when it was smaller, hotter, and denser, and it's been moving at light speed, those photons just moving through expanding space ever since. The future of that radiation is governed by the expansion history of the universe. The universe is currently accelerating in its expansion because of dark energy, and since dark energy is already the dominant force, and that dominance will only increase with time, we project that the universe will continue its accelerating expansion into the future. And that implies that the microwave background radiation will continue to be stretched or redshifted by the expansion at an ever-increasing rate. And logically, all that is really going to do is just lower and lower its energy as the wavelength is stretched by expanding space-time. And so things that are now microwaves, which are just, wavelengths of millimeters or maybe a centimeter, will gradually get stretched out to meter-length radio waves, then kilometer-length radio waves. I mean, if you project this into the infinite future, then the radiation just gets stretched and diluted to an incredible degree, but not actually to zero. The universe would have to be infinitely large for that energy to go to zero. So we just have a very slow degradation of the amount of energy, increase of the wavelength, and dilution of that radiation in an ever-expanding universe.
The next question is from Thomas Coverdale. Would you please explain the concept of zero-point energy and its relationship to the expanding universe arguments?
Zero-point energy is an idea out of quantum physics, quantum theory, which states that the vacuum, as measured in the lab and as part of the theory of quantum mechanics, the vacuum of space or any place that has no energy or particles in it does not actually have absolutely zero energy. There's a small zero-point energy, which is a fraction of the Planck constant. The Planck constant is in metric units is a very small number, 10 to the minus 27. And so there's this tiny amount of energy that exists in the vacuum of space. And of course that vacuum energy, this zero-point energy, has the potential to do things. This is the vacuum energy that we think can lead to the creation of particle-antiparticle pairs, which come in and out of existence all the time, as also predicted by quantum theory and observed in the lab. And this zero-point energy may or may not be associated with the vacuum energy that we think led to inflation and to the accelerating expansion in dark energy. It's not clear that we can connect our understanding of quantum zero-point energy in microscopic physics with these global, more cosmic signatures of something going on in the vacuum. The numbers simply don't work out at the moment.
The next question is from Parth Sarda, who asks, how do gravitational waves travel at the speed of light?
Well, you just have to imagine a wave or a disturbance traveling through a medium. If we have a water wave, we can understand how the water wave will travel with a certain speed, and that's due to the physical properties of water as it gets a disturbance in its surface. We can imagine how sound waves travel through air, and those are due to compression waves of molecules hitting each other and carrying that compression outwards. And so in the case of gravitational waves, it's a somewhat different situation, but it's the same idea, disturbance traveling through a medium. In this case, though, the medium is nothing at all. The medium is space-time itself. In other words, it's the context, it's the texture, it's the backdrop, the geometric backdrop, because space-time in general relativity is called a manifold, a mathematical concept. So that's what makes gravitational waves rather unusual, because there you have disturbances in space-time itself, and according to the theory of relativity, they will propagate at the speed of light. Now, that's not been directly tested, but it has been indirectly corroborated, since we've seen gravity wave signals from across the universe with large look-back times. But it's emerging from the theory of general relativity, the way these disturbances operate. And another unusual feature of gravitational waves that people tend to forget is that when we measure gravitational waves with something like LIGO, we actually measure the amplitude of the disturbance, the amplitude of the wave, as opposed to light or electromagnetic radiation, where we measure the intensity of the wave. Now, intensity is the amplitude squared, and that means the inverse square law applies for light and electromagnetic radiation, where the energy of the source, the energy you measure, goes down as the square of the distance from the source. In the case where you measure the amplitude, the intensity of the radiation or the disturbance only goes down linearly with distance. And that's part of why we can detect gravitational waves from such enormous distances, because they dilute or diminish in strength in a much shallower way with distance than light does.
Kind of a related, excuse me, and follow-up question is from Jake Johnson, who asks, so this is related to gravity. Can you explain if there are objects in space whose gravity will never affect us? I'm confused about how gravity is infinite.
Right, and that's an understandable confusion, because this was a problem, a conceptual issue with general relativity, going back to the beginning. So at the genesis or the inception of Einstein's theory of gravity, there were other major physicists of that time. It was a very golden era of physics, as you probably know, and especially in Europe and especially in Germany. There were other physicists who were wondering about this nature of gravity. Newton, for example, back to his theory, was asked, what is this amazing magical force that propagates through the vacuum, or it holds things to each other with no strings through the vacuum of space and appears to propagate instantly? He said, I don't frame a hypothesis, and basically said, I don't know. I just have a theory that seems to work and makes predictions, and they can be verified. I don't necessarily understand that. Einstein changed the theory to be gravity as something where mass and energy cause the curvature of space and time. But Einstein didn't solve this problem either. Ernst Mach, who was a very influential physicist, somewhat older than Einstein, around the turn of the 20th century, he came up with Mach's principle, which was a statement that the gravity of the entire universe, everything in the entire universe has to feel the gravity of everything else in the universe, because gravity is an infinite range force, whether you think of it as Newton's gravity or curved space-time. And so this issue of how everything in the universe can feel the gravity of everything else in the universe, and in the general relativity idea, curve space-time appropriately, is a conundrum. It's a logical and philosophical puzzle that actually hasn't been fully solved.
Excellent, thank you very much. The next question is from Sarah Mancusi. Do you have a favorite constellation to look at? Perhaps you can talk about some of your favorite objects.
Sure. Well, we're still in the winter, spring, and so I kind of like Orion in the northern hemisphere. Orion's even better in the southern hemisphere, but Orion's a really nice constellation. It's a classic one. It's very easy to identify. The stars in that constellation have, noticeably different colors. Aldebaran, which is a red giant, supergiant, is noticeably red, and then some of the other stars are much hotter and whiter. So you see a real variation in color. if you are in a really dark site, and certainly with binoculars and really good people can see it with naked eye, the Orion Nebula, it's pretty easy to see. So that's one of the, and that's M42, so that's one of the Messier objects. So Orion sort of got it all, and it's near the plane of the galaxy, so the Milky Way runs not too far away from there, so it's a pretty nice piece of sky. And it's even, as far as the constellations go, it's even less of imagination required to see the Hunter there and the Belt and the Sword. So it's a pretty virtual or sort of literal constellation, if you like.
The next question is from an email from someone who would like to know, is it possible to ignite a fire on Mars?
No, a fire could not be lit on Mars because there is essentially no oxygen, so there's nothing for the fire to combust with. And it's an important issue, actually, because combustion and fire is a major cause of damage to machines on the Earth, of catastrophes on the Earth. I mean, the fire damage around the world from things that catch fire and take flame is enormous, and it's all because of the oxygen. If you starve any fire of oxygen, you starve the fire, and combustion is not possible. And Mars has essentially no oxygen in its atmosphere. It also has a very low density atmosphere anyway. So it is not possible to have a fire on Mars.
So here's a question that asks you to speculate about something speculative, but it could be an interesting thought experiment. Tian Kuto asks, how would quantum fluctuations work close to a wormhole? Would it be something similar to Hawking radiation?
That's an interesting question. So a wormhole being a, ostensible portal in space-time between one part of space-time and another part of space-time, and it would require some significant curvature, of course, of the global space-time for that to pertain. Particle-antiparticle pair creation will happen near a wormhole, and so the question is, what is the operation of that principle, that physical principle of microscopic physics near a wormhole? So it's speculation on top of speculation, since we don't know that wormholes exist. I'm going to guess that the same mechanism whereby Hawking radiation leads to the implication of the evaporation of black holes and a small amount of radiation is going to apply to a wormhole too. So a wormhole at the point of it being what amounts to event horizon at one end will have its own Hawking radiation, will have its own temperature. Now the interesting question is whether that also connotes to black hole evaporation. So if you have an isolated black hole, the implication of Hawking radiation is the black hole eventually disappears. It's losing energy, it's losing mass, and evaporates with a crescendo at the end. Since a wormhole is a portal between points in space-time, possibly two black holes connecting to each other, then it's not clear what happens. If we follow the logic of Hawking radiation, it might be that the wormhole would eventually just disappear, that when the evaporation process continues sufficiently, the wormhole itself evaporates and closes up, basically, so you lose the wormhole.
The next question is again from one of our live participants. Parth Sarda asks, what do you think about the controversies that CPT symmetry may not exist?
Well, CPT symmetry is, you have to understand that first as a fundamental symmetry principle in physics, charge, parity, and time. So in quantum theory, most quantum properties are reversible in that we see opposite forms of those principles. So obviously we can have positively charged particles and we can have negatively charged particles, like a positron and its antiparticle, the electron. We can have parity inversion. So particles have spins. Now these spins are not literal spins the way a spinning top is. They're isotopic spins defined in quantum theory. But you can have spin orientations in one direction or the other, and that's parity. They are mirror images of each other in this spin, this quantum spin. And then time, obviously, in principle, is in our practical world is not reversible, but in the quantum world it is reversible, because any particle interaction or reaction that you see going forward in time, you can make to occur or actually see occur in the reverse direction. which is a symmetry principle of time. So the premise of physics for a long time has been that even while there can be small scale violations of one or two of these symmetries, the global symmetry of all of those three taken together applies. We know there is a violation of charge and parity, combined charge parity, CP violation. That's been seen in particle interactions for decades. But we've never actually seen CPT violation. So as a principle of physics, it still holds fairly well. People speculate, however, that in the theory of everything, in string theory and other overarching theories of particle physics, CPT violation might actually occur. We just haven't seen any experimental evidence for it.
Our Jason asks, why does the hydrogen-helium ratio suggest the Big Bang? Why can't this ratio be explained by fusion from stars of different sizes?
Yes, stars, of course, in their main sequence phase, like the sun is in the middle of, will be doing a fusion of hydrogen to helium in a three-step process. The proton-proton chain, that's a ubiquitous stellar fusion reaction. And there are a lot of stars in the universe. But now we have a census of stars and galaxies in the universe. We can pretty much calculate how much helium all the stars in the universe have made over the history of cosmic time, 13.8 billion years, in all the various galaxies they live in. It's not a precise calculation, but it's a pretty easy calculation to make because we know what fraction of stars are main sequence stars, we know how many are in the Milky Way, we can extrapolate to other galaxies. And you come up very far short of what is needed to account for a quarter of the universe being helium by mass. Also, this helium in the universe is seen in the intergalactic medium. It's seen in the spaces between stars and between galaxies. The helium made by stars, much of it, of course, doesn't escape. Stars only recycle some fraction of their material into interstellar space, and an even less fraction into the space between galaxies. So the helium that's made in stars does not get to the places it needs to be smoothly distributed through the universe. The only way for that to be explained is if the Big Bang made the helium, and so that's what we think is the answer.
The next question excuse me, is from 8 Koret Yug. How many stars can we see in the night sky with our naked eyes?
That's an interesting question. I've looked at that a little because I've heard arguments about that with amateur astronomers and online. The general number that's given for a moderately dark sky is 4,000 to 6,000. So that's a range, and that range essentially accommodates the variation in sensitivity of the human eye. So there are two variables in how many stars you can see in the night sky. One is how dark your sky is, and the other is how good your eye is. So the physiological variations in acuity of human eyes is significant. So amateur astronomers have had competitions or have done this in a sort of controlled setting of a very dark site where they've just seen how many stars they can variously count in certain patches of sky or constellations looking for the faint stars. And it's a significant difference. It is that 50% difference. The variation in how many stars you could see because of the sky brightness is an even larger factor, especially between urban and rural settings. But if you just assume you're in essentially a dark site, sea level site, high level might be even better. Unless you're too high, then you get oxygen starved in your eyes. So up to about 6 or 7 or 8,000 feet, you do gain by being in clearer, sharper air. Beyond that, you lose by oxygen deprivation in your eye. So 6,000 seems to be the practical limit.
The next question is from SpaceX, who's on with us live. What % of the universe is dark matter, and how do we even know that?
The percentage of the universe that's dark matter is roughly a quarter, 24% actually, in the most recent calculations. The normal stuff of the universe, the stuff we're made of, is about 4%. In other words, there's 6 times as much dark matter as normal matter. The normal matter is protons, neutrons, electrons, and then small residual amounts of more exotic or rare particles. The dark matter, the particles that outnumber normal particles by a factor of 6, we don't know what it is. we still assume it's a fundamental particle because larger objects that are dark have essentially been ruled out at this point. And so when we try and account for dark matter and understand what it is, we have to look for particles that are as abundant in the universe as protons, neutrons, and electrons. And that implies they have to be fundamental particles that are, definitely a simple extension of the standard model of particle physics. They can't be very exotic or rare or hard to create because there are so many of them. Astronomers and physicists are closing in, they think, on lab experiments and mine experiments to detect the dark matter particle directly, but that hasn't happened yet. So at the moment, it's assumed to be a obviously weakly interacting particle, weakly interacting with radiation, because it doesn't emit light, it's dark, but it exerts gravity. And so in the universe, we see the dark matter and measure that 24% essentially by how galaxies are held together by dark matter, how dark matter is distributed in clusters and on very large scales in the universe, and even how dark matter is distributed in the spaces between galaxies where it causes very weak amounts of lensing due to general relativity.
Ragnar Lodbrok, who's on with us live, would like to know what predominantly determines the direction that heavenly bodies spin. Is there an even 50-50 split of clockwise versus counterclockwise rotation of bodies in space?
Yes, that's a good question. And the presumption of the universe generally, in fact, it's called the cosmological principle, is homogeneity and isotropy. Homogeneity means the universe is more or less got the same things in it and from one location to another, talking about large scales now, tens or hundreds of millions of light years. And isotropy means that the universe looks more or less the same in every direction. Applied to rotation of anything, whether it's a galaxy or a planet or a star, this implies that we don't see any systematic variations in rotation of objects in one part of the universe to another, or looking in one direction to another. Not like we see objects spinning clockwise in one part of the sky and anti-clockwise in the other. And we essentially assume that on scales like a galaxy scale, the stars are randomly oriented and are spinning in different directions. Now the galaxy itself has an overall rotation, and it's possible that that overall angular momentum and rotation could impute a slightly higher probability to stars rotating in a way that's the same direction as the disk of the galaxy. We actually haven't seen any evidence for it. So it looks like small-scale turbulence and small-scale random motions dominate the formation of stars and their spins. Planets are the same, so because they follow the star spin when a solar system forms. So essentially, it's pretty clear, it's obvious in principle, and it's clear in measurement that these spins and rotations and the vector of angular momentum, if you like, are randomly oriented on all scales.
Thank you. The next question is from one of our live participants. As we know, after the Big Bang, the universe is expanding till now. So can we look forward at the universe collapsing after the energy fades out, like a reverse Big Bang?
So the future of the universe is still slightly uncertain, but we can imagine that we can predict it from the contents of the universe we see now, unless they change substantially. And the contents of the universe we see now, where dark energy dominates over dark matter, which dominates over normal matter, suggests the universe will accelerate and continue to expand forever. And that's a fairly reliable prediction. There's a slight caveat. The caveat is that we don't understand dark energy, so the accelerating expansion is caused by dark energy, which is a property of the vacuum of space. In other words, as space expands, the space keeps making more energy, so the absolute amount of dark energy in any volume of space stays the same, and essentially a constant over time, whereas dark matter dilutes and has less effect over time. If there was some decay in the dark energy and the strength, if there was something about the nature of dark energy itself that led it to change over time, then we lose our power to predict. But if dark energy has the properties that we observe it to have, and those properties do not change with time, the accelerating expansion is guaranteed. So if dark energy were to decay, as for example, as a hypothesis, then yes, it's possible that the dominance of dark energy currently would eventually be overcome even by the diluting amount of dark matter in the universe, and eventually the universe might reach a maximum size and then recollapse. But we don't think that's going to happen given what we know about dark energy at the moment.
The next question is from Elaine Remy, who asks, when Earth becomes uninhabitable because of the sun growing, will Mars become easier to geoform or terraform?
So yes, the future of the solar system has some interesting prospects. There's dramatic endpoints when the sun runs out of hydrogen at the end of its main sequence life, and it goes into a red giant phase. And at that point, the envelope of the sun will reach out to the orbit of Mars. So not only will the biosphere of the Earth be destroyed, but Mars will pretty much be uninhabitable. So if we wait till the end of the sun's life, then there's no habitation anywhere in the inner solar system. But on a shorter time scale, it's more interesting because as the sun gets towards the end of its supply of hydrogen and reconfigures itself, it actually burns hotter or fuses at a hotter temperature. And so the solar radiation will increase steadily with time, especially over the last 10% of the sun's life, the last half billion or 2/3 of a billion years. And at that point, indeed, the Earth will become uninhabitable. The surface temperature of the Earth will exceed the boiling point of water. Mars will, of course, start to get warmer. So yes, there is a little window in the future of the solar system where Mars becomes habitable, enters the habitable zone essentially because the sun's luminosity is going up. It's not much of a window. It's a couple 100 million years, out of a 10 billion year lifetime of the sun. And then after that, when the sun exhausts its nuclear energy and reconfigures and has some violent episodes, then Mars is uninhabitable. But there is a little window of time when Mars could be habitable without the enormous effort of terraforming.
World of Science asks, why don't we build a field detector which could detect quantum field interactions, which might be able to help us understand certain objects, I'm assuming like black holes or things like that, in great detail?
Well, our ability to detect quantum fields is kind of limited. We have mechanisms for detecting quantum fields associated with normal particles, for example. Those are quantum fields. We also can detect vacuum energy, which is a quantum field, and there are lab experiments to do that. But the diagnosis of quantum fields in the laboratory is still fairly limited. And of course, the physics is still under investigation. So I think it's just a very early days in that subject as an experimental science.
Excellent. The next question is from one of our live participants. Varun asks, there's a new buzz of the magnetic fields of the black hole image that came out recently, and some people who weren't with us last time probably missed our discussion of that. So can you talk a little bit about what the new data about the black hole image was released and what the significance of these magnetic field lines are?
Yes, the Event Horizon Telescope produced the spectacular image of a massive black hole, 6 billion solar mass black hole in the galaxy M87 last year. Spectacular success, and they've been continuing to gather data, and they've added telescopes to their array and improved their sensitivity. And with improved sensitivity, they can not only start to look at other objects, but for M87 they can get more detailed information. Now, the accretion disk around a black hole is threaded by magnetic fields. We are pretty sure that accretion disks are magnetized and that the particle acceleration along the field lines, especially along the poles of a black hole, is a wonderful mechanism for ejecting energy from a galaxy. That's what quasars are, essentially. So this image has enough signal to noise, enough sensitivity to actually see polarization of the radiation. Now that's difficult because the polarization of a few percent, say, which is the kind of level we're talking about, means you actually have to measure the intensity very accurately to measure a polarization of a few percent. So it's very challenging to measure polarization when the polarization is small. Polarization is an indication in the radiation. This is the millimeter radiation detected by this radio detector interferometer, is an indirect detection of magnetic fields, because when a plasma is magnetized, then the radiation is polarized that comes out of it. It's typically synchrotron radiation. So these observations are revealing the magnetic field that threads the accretion disk around M87, and it's helping our knowledge of how these objects accelerate particles and create phenomenal energy at the center of galaxies. M87 is not a very active galaxy in the sense of a quasar. It's not a quasar. It's a giant elliptical galaxy with a radio source and a big black hole. It's actually rather quiet for a big black hole. But this is a great view into it, and I think it's going to improve our models of how energy gets out of the region around a black hole.
Excellent. The next question is, again, from one of our live viewers. Chandran Pushparatnam asks, I understand gravity waves may have been detected by pulsar timing before LIGO. Can you please explain this method of detecting gravity waves?
Sure. It's a very challenging technique that has moved forward quite rapidly. LIGO, of course, spurred the whole field of gravitational waves, and they now have dozens of events. Pulsar timing was conceived of a long time ago, decades ago actually. And the trick here is that pulsars are excellent clocks. And so by excellent I mean they're accurate to 1 part in a trillion or less. And so what happens when a gravity wave passes over a pulsar, passes through a pulsar, is it tweaks or perturbs the timing of the pulsar because the space-time is actually being distorted. So as the wave passes through the pulsar, the pulses from the pulsar are actually very slightly altered in their timing or frequency. And it's a very subtle effect, but the pulsar timing precision is very high. And so basically with an array of pulsars, a set of pulsars distributed around the galaxy, you can measure their frequency of their pulses with this very, very high precision and see by essentially triangulation whether a gravity wave may have passed across this field of pulsars. That's a principle. To do this work well, you need a whole grid of pulsars, dozens or maybe even hundreds eventually, and we're not there yet. But people have prototyped the method, and it does now apparently have the sensitivity to detect the kind of gravitational waves we expect to be in the universe, which is very exciting.
The next question is from Dimitris, who's on with us live. Have we implemented the parallax method in any of the probes orbiting Jupiter or Saturn to measure more accurate star distances or calibrate other distance measurements methods?
The probes that we send around the solar system are not really designed or configured to do parallax measurements very accurately. But there is a mission that is doing this with exquisite precision. It doesn't get as much airplay as Hubble Space Telescope and the other facilities, but it's a spectacular mission by the European Space Agency. And this is the Gaia mission. So there was, back in the 80s, there was a position measuring satellite called Hipparcos, which is named after the astronomer from antiquity who made the world's first stellar catalog. And Hipparcos measured the positions of motions in space, positions and parallax and space motions through velocities of about a few hundred thousand stars, ranging out to maybe a few hundred light years from the Earth. Gaia is doing a spectacularly better job. It's an incredibly precise mission. It has 26 cameras, I think, each with a fisheye lens pointing in different directions. It's mapping enormous numbers of stars, quite faint. And its goal, when it's finished in a few years, it will have measured the positions and space motions, so parallax, and then the distance, to about 1 billion stars in the Milky Way, out to distances of thousands of light years, essentially 1% of the stars in the Milky Way. So orders of magnitude improvement on the previous space mission. And so that's going to take parallax to a whole new level. And it does this by making measurements with a precision of about 20 micro arc seconds. That's 20 millionth of an arc second. So it's, again, spectacular accuracy that's required, of course, to measure parallax for stars at distances of thousands of light years.
All right, the next question is from CSUN Scientific, and it has an assumption baked into it, but we can kind of pick this apart and discuss it. Can you explain how the alternate universe works?
Well, let's talk about whether an alternate universe exists or makes sense or is part of modern cosmology. The conventional cosmology holds that the space-time around us is the only space-time that exists. It's the only one we can measure. So when we look out in space, we do not see an edge to space. When we look out in space with deep observations and big telescopes, we see back in time. And the limit of our view is actually a limit in time as we look towards the Big Bang. We don't run out of space. So there's no sense from practical observations in cosmology that the universe we live in has a limit, has an edge. And so right away you have an obstacle imagining an alternate universe because there's no edge to our space-time and no part of the theory except the multiverse idea, which I've mentioned earlier in other question times, that there are even other space-times. So basically, the conventional view is there is no alternative universe. This universe is the only one, the one we see, the one we can observe. Only in speculative parts of cosmology where we try and address the quantum nature of the Big Bang event, which is a reasonable hypothesis, but the implications of that hypothesis are not clear. So it's not at all clear how we can talk about other space-times or alternate universes or what their properties might be. It's definitely speculation. There's nothing wrong with speculation in cosmology, but there's still some pretty basic things we don't know about the universe we live in. So most cosmologists are more worried about answering those questions first.
One of our live participants would like to know what are the new methods being introduced by different organizations to deal with the catastrophe of space junk?
Yeah, space junk is a big issue. There was a paper that was put on the preprint server just recently from European astronomers that was essentially saying that astronomers have sort of underestimated the degradation of the sky brightness due to space junk, due to satellites and microsatellites, that it's sort of worse than we imagined or had calculated or estimated. And so this is a real problem, and there's no simple answer to it. So it's twofold. There's the issue of the space junk that's already out there, the fact that when pieces degrade or there are collisions and you get a lot of small pieces from one large piece, that can only go in one direction. And it just increases the amount of space junk, which in turn increases the probability of collision, which increases the probability of more space junk. So it's this cascading effect. And that's just if you put nothing else up there, because almost none of this is being deorbited or brought down. It's just sitting there. And then there's the increase in space junk caused by the robust and rapidly growing industry of putting small satellites in orbit. The only saving grace for many of those projects, including the one by SpaceX, is that these are in very low Earth orbits, low enough orbits that they actually, through drag in the very thin upper atmosphere, deorbit naturally after 5 to 7 years. So some of these nanosats and microsatellites are going to naturally clean themselves up over time. I think the deeper problem is the stuff that's in low Earth orbit from 200 to 350 miles, which does not deorbit in any reasonable time, and which is still getting worse too, because we're putting more satellites up there too, and the collisions will continue to happen. And astronomers nor other technologists don't have any really good answers to this, mostly because the interested parties are not really working hard enough on it or committing to it as a big problem. Eventually, I think they'll have to. The technology solutions are not obvious because space is big. Even in low Earth orbit, the volume we're talking about and the spacing of the pieces of debris is so large that there's no easy mechanism to sweep it up or scoop it up.
The next question is from one of our live participants who would like to know if which fictional movie do you feel is the most realistic in portraying some aspect of space exploration or technology?
Well, I'm partial to The Martian because that was done very well. It was written by a former planetary and space scientist who, understood exactly what the habitat of Mars was like, made plausible speculation as to how we might live there or live there in a colony or, grow vegetables, if you like, or and so that movie, the book that it was based on, and then the movie made from it, is full of very plausible space science and planetary science. That's the most recent movie I know that gets the science pretty right.
The next question is from Tena, who asks, so she asks, or they ask specifically, how are your work and research about astronomy going during quarantine? But in general, maybe you can talk about how astronomical research has been affected by the pandemic and by quarantine.
Yeah, the quarantine and the pandemic have had a serious impact on astronomical research. For my part, not so much, because my sort of days of using big telescopes routinely are pretty much over at this point. I move more into education and technology work, and that's more self-contained, so I'm less impacted. But for observation, and theorists, of course, are not as impacted. But for observational astronomy, the impact has been quite substantial. For a large part of 2020, the major observatories, our major observatories in Arizona, our partner observatories in Chile, and most of the world's observatories elsewhere, like in Mauna Kea and Hawaii, were essentially closed. That is closed to visiting astronomers and to engineers and to routine operations. Now, many telescopes, of course, the large telescopes, are designed to work remotely, so the astronomer doesn't have to visit, and that's okay. But people sort of forget, when they think about remote observing and how that shouldn't be affected by the pandemic, that large telescopes are state-of-the-art, complex engineering facilities, not just the telescope itself, the instruments that hang off it that have to be exchanged every few days, the parts of the telescope that have to be changed, the secondaries, all the engineering work. I mean, there's huge labs and engineering works attached to big telescopes, and you have to have a crew to manage that. And if you're in situations where you're not allowed to be in groups or significant numbers of people, then there are safety issues. So a lot of the closure of major observatories were due to the safety issues, that you can't operate these observatories safely without having teams of engineers, scientists, telescope operators, etc. And when people were not allowed to work in proximity for a while, that really shut everything down. Things are opening up now, and so probably half of our large telescopes are now operating remotely, and many of them operated remotely anyway. And worldwide, it's about the same thing. But I'd say astronomical research took a substantial hit for about a year. Now, space-based research is quite different, of course. That's always done remotely, and so that's essentially been unaffected. Use of the Hubble Space Telescope, for example.
The next question is from Art Studio, who's on with us live. Have we detected W and Z bosons in the universe? And I'm assuming they mean like separate W and Z bosons, but perhaps you can just address it generally.
Sure. So the W and the Z bosons are the carriers of the weak force, one of the four forces of nature, which are in decreasing order of strength. A strong force that binds the atomic nucleus, the weak force that's responsible for destruction of the nucleus and radioactivity, for example, the electromagnetic force that's responsible for radiation and light, and gravity, the weakest of those four forces. In the 1970s, and actually one of the experiments I was involved in when I was a physics student in London, I worked at CERN for 2 summers, and I was on an experiment that was working on what were called weak neutral currents, which are collision experiments with the CERN accelerator of the time. This is before the LHC. That was designed to tease out the W and the Z particles. So there are 3 bosons that are associated with the weak force, and they were all detected individually or working together in conjunction in collisions in the late 1970s, and they led to the award of several Nobel Prizes, I think maybe even 3 or 4 over a decade. So yes, we have observed the W and Z bosons for the weak force, and that was one of the major triumphs of particle physics a few decades ago.
The next question is from Dennis Baller, who asks, why is the Earth-Moon system considered to be a planet and moon system and not a binary planet system?
It's a close call. As most people know, the moon is a very large satellite relative to the planet that it orbits, by far the largest satellite of any planet relative to the planet in our solar system, and we think it's unusual in general. And we think it's that way because the moon was created by a collision of the proto-Earth, if you like, with a Mars mass object in the crazy phase of the solar system in the first 50 or 60 million years. So it's an anomalous formation mechanism rather than a debris disk forming around a planet that leads to much smaller moons and potentially ring systems. So it's an unusual formation history that led to the moon being as large as it is. At some level, yes, it becomes a matter of semantics, whether a moon is large enough to actually start calling it a planet. But of course, as anyone who knows the debate over the status of Pluto will know, astronomers tend to have a set of regulations by which they define a planet, and according to those regulations, the same ones that demoted Pluto to the dwarf planet status, the moon does not qualify as a planet or a dwarf planet. It is a satellite of the Earth.
Excellent. The next question is from Lawrence K. Can you explain the so-called crisis in cosmology and talk about whether or how gravity waves might help resolve it?
Yeah, the so-called crisis in cosmology is a disagreement between measure the expansion rate of the universe from local observations, that is, measurements of the expansion rate in the nearby universe. By nearby, I mean tens of millions of light years, so local clusters and supercluster. And the expansion rate of the universe inferred from a cosmological model fitted to the microwave background. These two things should be consistent, because if we think we understand the contents of the universe, then we can tell the story of the expansion history of the universe. And the expansion rate, of course, has changed over time, but the contents of the universe dictate the expansion history, and measuring that expansion rate now and in the distant past, they should be consistent with the same cosmological model. They're not, and that's been a persistent problem that's led to this crisis. And that crisis hasn't really abated or gone away. Each side has sort of dug in and had more data and really affirmed their original position. So the discrepancy between these two different measures of the Hubble constant essentially has not gone away. It's not clear if gravitational waves is going to be the way we solve this problem. The gravitational waves eventually we hope to detect from the universe itself, from the Big Bang. So maybe there's something about the Big Bang, some ingredient of the Big Bang, or some early initial conditions that we don't fully understand. Gravity waves may have something to say about this. The other possibility is that the answer is closer to home. It's possible that the local universe is anomalous in some way, that we live, for example, in a huge bubble, which would give you a systematically different expansion rate if you lived in an underdense region compared to the cosmic average. There are hints of that, but no confident indication that there's anything anomalous about our position and local environment, which would be a violation, of course, of the Copernican principle. So this is a problem that doesn't really have an easy resolution at the moment.
The next question is from Ayush, who asks, how does plasma exist in space, or really how does any atomic particle behave in vacuum space?
So plasma, by its definition in physics, is just a medium where the particles, the electrons, have assumed, knowing that the universe is mostly made of hydrogen, we can just talk about hydrogen atoms, a medium where the temperature is high enough that the electrons are not attached to the protons is formally a plasma, and by extension, for helium, the second most abundant element, electrons are not attached to helium nuclei. And so the temperature required for that condition is known by physics. In the universe, the interesting part of this situation is that the density is very low. So you can have a high density plasma that can be created in the lab quite easily. But this is a very low density plasma, because the space between galaxies is extremely low density. It's about one hydrogen atom, one proton per cubic meter. So incredibly low density. And yet there are electrons in that same volume, and the electrons are not attached to the protons. And so it's formally a plasma. And if you calculate the kinetic energy of these particles and attribute a temperature to them, the temperature is hundreds of thousands or a few million Kelvin. And we've now actually observed X-rays from this intergalactic medium. So we know it's a plasma because we've seen the X-rays we would expect from a diffuse medium that's really this hot.
I'm not quite sure which one of these to address first, but I guess I will start with Art Studio's question. What do you think is the information, the amount of information in the universe increasing as it expands and as entropy increases?
Oh, that's an interesting question because information and entropy are formally related in physics terms. We don't think of information in a physical sense. Usually we think of information as, bits and bytes stored on, USB drives or hard disks or whatever. But information in the universe is related to entropy in a direct sense, that entropy is colloquially disorder, but it's the number of microscopically equivalent states of a system. And when the number of distinct microscopic states is obviously at some level related to information storage, because if you have distinct microscopic states, then in principle you could use them to store information. If the states are indistinguishable, then there's no way to store information in them. So that's generically how entropy and information are related. In the expanding universe, and according to the laws of thermodynamics, the entropy or overall disorder is increasing. And so in a sense, the information content of the universe is degrading with time. And that's because everything is eventually in the final situation where galaxies and stars evaporate and particles decay. We're going to end up as a particle soup where there's very little structure, of course. And so without structure, there's no way to hold information. And the degree of disorder or entropy is very high. So that's the way we think things are headed.
So then I guess the answer to the next question, which you can address a little bit, which is it correct, would it be correct to say that the information in the universe is infinite? It sounds like that's not the case.
No, the information content of the universe cannot be infinite because actually that's logically impossible, because there's no way a physical space-time can have infinite information or infinite energy or infinite anything, and our space-time is not infinite. We are bounded in our view of the universe by the horizon, so we're not dealing with an infinite space-time, an infinite amount of matter, or an infinite amount of energy, so there's no infinite amount of information. We cannot really speculate on the possibilities of space-time that we can't observe, which indeed could be there because the universe has expanded faster than light speed for some of its history. But there's no logical way to understand infinite amounts of energy in a finite universe.
All right, it is 10:58. We'll see how long this question takes. We may be able to take, two more, but this is going to be at least the second to the last question. Thomas Coverdale asks, there's one comment in the readings that bothered me, and it said that if the universe has an edge in time but not in space. Can you talk about what that comment means?
The edge of the universe in being in time, not in space, simply relates to the fact that as we look out with our telescopes, so it's just a purely practical thing of observation. If we look out through telescopes as deep as we can, the biggest telescopes, Hubble, biggest ground-based telescopes, there's in no point at which we see an edge of space. I mean, if there were an edge, in principle, we could see it if we look far enough out, and we don't see it. We don't ever see it. What we do see, however, is that as we look out in space, we look back in time, and eventually we run out of galaxies because we're looking back in time towards the era when galaxies first formed. So that's why operationally, because of look-back time, the edge to the universe that we see, if any, is an edge in time, meaning the origin in the Big Bang, and there's no evidence for an edge in space.
All right, so that was quick enough that I think we have time for this one last question, which is from World of Science. And there's kind of an assumption built in here. The question is, why aren't we able to measure the rate of the expansion of the universe accurately? But I think the real, underlying question is how accurately are we able to measure the expansion rate of the universe, and is that sufficiently accurate for what we would like?
Right, that's a good general question. Measuring the expansion rate of the universe is hard because it's been done historically in the nearby universe. The Hubble constant is the local expansion rate on scales of tens of millions of light years. It was done first well. Now, historically, going back 50 or 60 years, astronomers disagreed by a factor of 2, so 100% error in the expansion rate. There was a big argument over the Hubble constant back in the 60s and 70s. With the Hubble Space Telescope, one of its 3 initial key projects was to measure the Hubble constant to better than 10% precision. And with some difficulty, it took years and hundreds of hours of observations using Cepheid variables in nearby galaxies as the distance indicator. It did measure the Hubble constant to about 10%, slightly better actually, about 8%. So that was the state of play in the 1990s. Now since then, astronomers have tried to increase the precision of measuring the expansion rate. The reason you just can't pile on more data and just get better and better and better over time is that there are systematic errors as well as random errors in distance measurements in the nature of Cepheid variables if you use them, or supernovae if you use them. So there's sometimes astrophysics you don't understand well enough, and that's a big danger in distance measurements in general. The whole history of the subject is full of that danger. Hubble himself vastly miscalculated the Hubble constant, the thing named after him, by an order of magnitude because he didn't understand Cepheid variables well enough. So there's big warning signs attached to this field. And I would say in the current era, the astronomers are pushing hard to get the precision of measuring the expansion rate down to about under 5% or 3 or 4%. That would be a goal. And it's really hard. It has taken years to get from 10% to under 5%. The eventual goal is about 1%. At that point, you can start to see very subtle effects in the cosmic expansion history, but we're not there yet. That goal of 1% precision is probably a decade or more away. So thanks again, a lot of good, varied questions. We'll be back with you next week. I think we've got the next one scheduled, so thanks to Matthew for facilitating, and we'll see you soon.
Excellent. Thank you so much for joining us, everyone. Just a last quick reminder that we will be sending out information about several live streams for the Yuri's Night celebration that will be happening April 12th. There will be one that we'll host on Twitch, and there will be another that is hosted by the University of Arizona, Steward Observatory, and Flandreau Science Center. We will send that information as soon as we have it. So thanks all for joining us, and next week will be at the same time on Wednesday. Take care, everyone.